So to solve this first one, I am going to just break it out, right? My index here is a 2. Remember, if you don't see one, your index is a 2. So that means anything that groups by 2s can come out, which means that can come out, which is where we got that 3. And this has to stay inside, which is where we got the 2. For the variables, I always just do my division. So I have x to the 7th. I'm going to say 7 divided by 2. 2 goes into 7 3 times with the remainder of 1. So 3 represents how many x's come out. 1 represents how many x's will stay in. I'm going to do same thing with the y to the 4th, y to the 9th, sorry. And I'm going to say 9 divided by 2, that is 4 with the remainder of 1. 4 represents how many y's I took out. 1 represents how many y's stayed in. Again, my index on 31 is a 2. So I can do the same thing I would do with my variables before. I'm going to do, I have x to the 6th and y to the 6th on top. If I divide that by 2, that's 3 with a remainder of 0 for both of them, which is where I got x cubed and y cubed, and nothing stayed inside. For that denominator, hopefully this is one of your perfect squares that you know. The square root of 100 is 10, which is why we got that 10 in the denominator. Then let's look at the last one. So for this one, my index is a 5. So I'm going to look at everything in terms of 5. When I do my factor tree here, 2 and 16, this is actually a perfect fifth root. All right, 1, 2, 3, 4, 5. That is a group of 5. So that's where I can take a 2 out. If I look at my variables, my a was to the 5th power. Again, I am dividing by 5, 1 remainder of 0, which is why 1a came out and I didn't have any a's that stayed in. For my b's, that was to the 15th power. 15 divided by my index of 5 is 3, remainder of 0. 3 came out. I didn't have anything that stayed in there. The product rule of radicals. If radicals have the same index, all right, so first step, if they do not have the same index, you can't just randomly multiply them. But if they do have the same index, then if you are multiplying radicals, you simply multiply what is inside the radical. So if I have the square root of 2 times the square root of 6, I am going to get the square root of 12. It's just simply the square root of 2 times 6. All right. Here's the thing. We're always looking to simplify these. So if I want to simplify this, then I am going to do my factor tree and go from there. It's great when you have something small like this, right? My index is a 2. That means those come out, that stays in. I end up with 2 square root of 3, all right? So that's one way to do it. Just go ahead and multiply and keep going. What I typically do when I am multiplying radicals is I go ahead and factor them before I multiply. Because the larger the numbers get, the larger your factors are going to get. And so 2 and 6 are easy. You can quickly do that factor tree when you get 12. But you'll notice the first row of my factor tree was my 2 and my 6. Because those are factors of 12. And so what I typically do is I will break these out, realizing that all of those will be factors of my product, right? So before I ever multiply, I go ahead and factor them. And then I can look at any grouping within all of those factors. So I can say, well, I know I'm going to have a pair of 2s, and I know I'm going to have a 3 that stays in. I'm going to end up with the same exact answer. I just didn't multiply first. I just went ahead and did my factors first. Because 2 and 6, I like the 3 factors. But if I were to multiply 24 and 12, then all of a sudden I'm having a whole bunch of factors. I don't want to multiply 24 and 12 and get a huge number and then do a factor tree on a huge number. I'd rather do 2 smaller ones and take all my factors of all of them. And so if you look at, for example, the next one. For this one, I don't necessarily want to multiply 18 and 50 and then do a factor tree for that big, huge number. I probably want to go ahead and do my factors first. A couple things about this one. I have numbers in front. Those are already on the outside. they're just going to stay on the outside. So I automatically know I have a -2 on the outside and I have a +5 on the outside. That's automatically there. For the rest of it, I'm going to do factor trees. And so I'm going to do a factor tree for my 18. And then I'm going to do a factor tree for my 50. My index is 2. So anything among all of those that groups can come out. So I can see I'm going to have a 3 that is also on the outside. I am going to have a 5 that is also on the outside. And I have, while they're separated, those are pairs of 2s that are also going to be on the outside. And I actually have nothing left on the inside here. This is going to end up being a perfect square root when it's all said and done. But instead of multiplying 18 and 50, right, and getting like 900, and then doing factors of that, I'm just going to do factors of my smaller numbers and pull all of the factors. And then you're just going to multiply -2 times 5 times 3 times 5 times my 2 there. And multiply it all out. When I multiply all of this out, I'm going to end up with -300 as my final answer. So if I multiply this times this and simplify it, I would get -300. Look at this one. I have 6ab times 2bc. So again, you can multiply it. You'll get 12ab squared c. All right? Or you can go ahead and factor them. 6 is just 2 and 3. I have 1a there. I have 1b there. I have a 2. I have a b. I have a c. Those are all primes already. If I look at what pairs up, 2 and 2 will pair up. I also have a b and a b that will pair up. I have things that are not pairing. 3 will not pair with anything. A will not pair with anything. And C will not pair with anything. And so if I look at all of my primes of all of them, then I don't have to actually worry about doing anything else. I will say with variables, sometimes when you have larger variables, I will just write those out to the side. So I have an A, I have a B times B, and I have a C, and I'll do those individually. I have one of those, I can do my division there, I have one of those. So if you have larger exponents, sometimes it's easier to go ahead and combine those and just do your division rule, divide by your index. But when you're multiplying numbers, it's typically easier to just do your factors. If I look at this, I don't think any of us want to multiply 225 and 315 and then do a factor tree, right? But if I look at this individually and I say, okay, they're large numbers, but I could potentially do factor trees on them individually and then go from there, then I can see, okay, this guy is going to be divisible by 5. So I can just do 5. 22 divided by 5 is 4 with 2 left over. 25 divided by 5. Go from there. And do the same thing for this one. Again, this is also divisible by 5. 31 divided by 5 with a remainder of 1, right? Something like that. All right. And so when I do it like this, then I am looking for something that groups in 3s. I have a 5, and a 5. That's a group of 3. I have 3, 3, and 3. That is also a group of 3. And then you'll notice I have some that won't group. I now have a 3 that's by itself. I have a 7 that's by itself. And so on the inside there, I'm going to have the 3 and the 7. And then I'm just going to multiply. 5 and 3 is 15. Cubed root of 3 and 7, 21. And that's going to be way easier than multiplying huge numbers and doing some huge factor tree for those numbers, right? As long as they're being multiplied, then all those factors apply to that index that you're looking for. When you're doing something with larger exponents of variables, you can still do the technique where you factor your numbers, but I would go ahead and combine those exponents and then use that division by your index there. So if I were to just have a number on the outside and variables or whatever on the inside, you would hopefully know at this point to simplify this means to distribute, okay? And so now I'm distributing with radicals. So I'm going to apply the principles of distribution as well as the principle of my radicals here. So if I have square root of 5 times this binomial, I'm going to say the square root of 5 times the square root of 3, right? And then to the next one, it's going to be a minus the square root of 5 times 2, all right? You can only multiply outside and outside and inside and inside. By that I mean square root of 5, square root of 3, the 5 and the 3 are both on the inside. They're actually both prime. So if I could simplify that like I've been doing, I would simplify that. But 5 and 3 aren't going to simplify. They're both prime. So this is going to become square root of 15. For this next piece, however, 5 is on the inside, 2 is not in a root. So I can't multiply those at all. I'm simply going to write it 2 square root of 5. All right, and that's how I'm going to leave it. I cannot combine those because they're not like radicals, okay? So if I were to add or subtract those, it's a square root of 15 and a square root of 5. I can't do anything else with that. I can't simplify my 15. That's 3 and 5. Nothing pairs up. I can't simplify the 5. It's a prime already. It's not going to have anything that comes out of it. So this is my answer right here. That's my answer for those. The next one's a little bit different, all right? So with this next one, I'm still going to use distribution. So I have 2 square root of 6 times the square root of 15, right? Then I'm going to subtract what happens when I say 2 square root of 6 times 3 square root of 10. Now I have outside numbers and inside numbers. So if I simplify this, I have a 2 that's already on the outside. That's going to stay out there. When I look at my radicals, I can actually do something with these. 6 is 2 and 3. 15 is 3 and 5. So I have something else that's going to come out here. That 3 is going to come out, right? And then on the inside, I have a 2 and a 5 that's going to stay on the inside. And remember, we're going to end up multiplying those. Let's look at the next one. All right. For this next piece, I have a 2 and a 3 that's already on the outside. Those are both going to stay on the outside. And then if I do this, 2 and 3, 2 and 5, I actually have a pair here. The 2's pair up, right? So I can actually pull another 2 out. And then I have a 3 and a 5 that do not pair. So inside I have a 3 and a 5. So I'm just doing it piece by piece. What pairs up, what doesn't, what's outside, what's inside, etc. Once I've decided all of my numbers that are outside and all of my numbers that are inside, I'm just going to multiply them to simplify. So I'm going to say here 2 times 3, that's a 6. And then 2 times 5, that's 10. Here I have 2 times 3 times 2, that's 12. And then 3 times 5 is 15. And that is going to be my final answer here. I cannot simplify that anymore.